Diffusion models are state-of-the-art generative models that have shown massive success in creating realistic images and audio. They work by learning to reverse a noising process that turns data into pure noise. The end result is we're able to gradually transform pure noise into data, and therefore generate new high-quality samples. Diffusion models take their inspiration from stochastic processes in physics. We can visualize the noising process as what happens when we drop a sugar cube into a cup of water. The sugar molecules all undergo random motion, and as a result, the distribution of molecules will generally smoothen out and settle into some maximum entropy steady state. This is exactly what happens in a diffusion model. The Ford process takes our unknown data distribution P star and keeps adding noise until it settles into a known base distribution P pi, such as a unit Gaussian. But the real magic happens in the reverse process, where we can use deep learning to gradually undo the noising process and transform our base distribution back to our data distribution. This is the fundamental idea of diffusion models. Now, these models typically work by constructing the noising and generative process as discrete time Markov chains. However, in physics, we typically model diffusion as a continuous process, using the language of differentials, such as in this Ito equation for stochastic motion. Here we have a drift term and a diffusion term, echoing similar terms in the DDPM update rule. Therefore, our Markov chains can be seen as discretizations of an underlying continuous process. It is therefore natural to ask whether we can actually capture this reality and explicitly model our forward and reverse process as continuous. In other words, we'll be constructing continuous time diffusion models where the noising procedure follows an Ito process. It turns out that doing this has several practical benefits, and we'll explore them in the next video in the diffusion model series. But there's also one major theoretical benefit, and it's this equation. To understand why this equation is so important, recall that since the Ito process is stochastic, we have a probability distribution over x that evolves with time. And in a diffusion model, this evolution is designed such that it transforms our data distribution to the base distribution. Now, remarkably, there exists a second Ito process whose probability density evolves in the exact opposite direction, retracing our steps back from the base distribution to our data distribution. This is given by the reverse time SDE, and it allows us to find the exact reverse process that we need to generate samples. Now, the only challenge is that we'd need to predict this score term here, but in the last video, we saw that training a DDPM with our noise prediction loss already enables us to predict the score, so we already have a framework for score prediction. Now, the astonishing thing about this equation is that the reverse of an Ito process is in fact just another Ito process, with an identical diffusion term and a modified drift term. It turns out that we can express the noising process of the DDPM and noise conditional score network as discrete special cases of our forward time SDE, meaning that the reverse time SDE can be applied to those models as well. So this equation is remarkable in many ways, but where does it actually come from? In this video, we'll find out. This is video 3 of a 9-part video series on diffusion models. In this series, we cover everything from theoretical foundations to practical implementations. In the first video, we covered the basics of diffusion models, and in the second, we saw how the DDPM objective is equivalent to score matching. In this video, we're going to derive the reverse time SDE, and this will prepare us for video 4, where we take a look at continuous time diffusion models and discuss their practical benefits. Now, there are 3 main elements we need for our derivation. The first is the Ito equation, and it's worth deconstructing a little bit before we move on. So, as we saw before, it is composed of a deterministic drift term and a stochastic diffusion term. In the diffusion term, we have this dW, and W here just represents a Wiener process. Put simply, a Wiener process is a continuous process with independent Gaussian increments that begins at the origin. So you can think of this term as continually injecting Gaussian noise into our dynamics. Now, the second is what's called the Kolmogorov Ford equation, or Fokker-Planck equation in physics. and this tells us how the probability density of an Ito process evolves with time. Now, this equation applies no matter what the starting distribution was. So imagine that we take snapshots of the density at time t and time s, with corresponding variables xt and xs, and s being greater than t. Now, the forward equation applies when we take the derivative with respect to s, for any arbitrary density that existed at time t. This means that it also applies if we set a Dirac delta function at time t, which gives us a conditional distribution at time s. So we've demonstrated that the forward equation is equally valid for the marginal and conditional densities at time s. But what about the joint density? Well, now we can just apply the chain rule and cancel the second term, since the marginal at time t does not depend on s. Then we can take the marginal into the derivative to find that it too evolves under the forward equation. So our marginal, our conditional, and our joint all evolve with the Kolmogorov forward equation when derived with respect to s. Now, this is good news for us. We've just shown that the forward equation governs how the joint density changes when we nudge s a bit into the future. So to find an equivalent evolution law for the reverse dynamics, all we have to do is nudge t a little bit into the past. To find this, we can just apply the chain rule, differentiating with respect to t this time. Now we can see that this marginal derivative follows the forward equation. However, our conditional derivative does not, because now we're differentiating with respect to the earlier time point. So now we're nudging t forwards in time, so our Kolmogorov forward equation does not apply. But as it turns out, we do have a special equation for just this scenario, and that's our third element, which is the Kolmogorov backward equation. So now we have everything we need to launch into our derivation. But first of all, we're going to define some shorthand notation, and this will prove very helpful when our expressions get very long. So here we have our joint distribution j, conditional distribution c, and marginal p. So the chain rule for our joint derivative can be expressed very succinctly like this. Now remember, the goal of our derivation is to find the negative of dj over dt. So first, we'll have to work out a form for this derivative. So we start with our chain rule expression, and now we can re-express the derivatives using our forward and backward equations. Now we can work the algebra and eventually separate out the terms according to whether they have the drift or diffusion coefficients. Now let's just focus on our drift terms for a while. First of all, we can use the product rule to expand our divergence of PF, then group some terms here. Now we can look at this first term and realize that this is just the gradient of Cp, so now we're doing a product rule contraction. Now we can actually contract again and realize that this is the negative divergence of Jf. So we can sub this into our equation for dj over dt. So now let's shift focus to our diffusion terms. First, we're gonna expand this double divergence using the product rule. Then we're gonna expand the trace term, and here we're relying on this standard identity, which I've called the trace product identity. And in fact, this identity is just the product rule, but I've packaged it into this form for convenience. So now we can just rearrange our terms like this. Now we can apply the product rule again on 3 of our terms, then cancel out these 2 terms, and we end up with this. Now it turns out that we can actually cancel 2 more terms here, but first we'll have to rewrite this dot product using a standard rule. And we can work the algebra to get this, and now since D is symmetric, it equals its own transpose. So we can write our equality like this, which means we can actually cancel these 2 terms from our expression. So now we have this. Now if we look at these 2 terms, it looks like they could have been generated using the product rule, except that one of them has a minus sign. So we can just do a product rule contraction, but with an extra -2 term. Now we can again contract to get a double divergence term, and then take the 1/2 into the bracket. So now we have this for our full derivative. The next thing we can do is work on the gradient of the conditional here. So we can apply the quotient rule and split the terms, then realize that the gradient of p over p is just the log gradient of p, or the score of p. So now we can plug this into our expression, split the divergence, and expand the double divergence using the product rule. Now we can combine these two terms to simplify our expression further. From here, we can do another product rule contraction, then take the 1/2 into the bracket, and combine these three into one big divergence term. And now comes the good part. If we just negate this expression, we find that we've actually just reproduced the form of the Kolmogorov forward equation. Now, quite strikingly, our expression has the exact same diffusion term as the forward equation, but with a modified drift term. This reverse drift includes the negative of the forward drift as well as a score term. Now, what this equation allows us to do is construct a reverse time Ito process using f bar instead of f, and with a d minus t to simulate a reverse time variable that increases with decreasing t. We also have a reverse time Wiener process here, and it's just the same as the Wiener process, but operating backwards in time. So now we have the full form of our reverse time SDE. And there we have it. We've now seen how to derive this foundational equation from the ground up. This is the exact equation we're going to use in continuous time diffusion models, with the only modification being a design choice of a scalar diffusion coefficient. As we'll see, this equation can be combined with denoising score matching to create a fully working generative model, and that's what we'll look at in the next video.